World War II was the most devastating conflict in human history, with a death toll of over 70 million people. The war finally came to an end with the bombing of Hiroshima and Nagasaki. In the second year of the war, the Manhattan Project was started to produce nuclear weapons in hopes of ending the war sooner. Their idea was to create an atomic bomb that would split heavy uranium 235 atoms to release energy. Did you know that the peak temperature that was observed at the nuclear fission explosion of Hiroshima bomb was approximately 60 million degrees Celsius? To put this into perspective, the temperature of our sun's center is 15 million degrees Celsius. That means this temperature was almost 4 times larger. This posed a serious question. Physicist Edward Teller asked, if we create temperatures hotter than the center of the sun in our atmosphere, will that heat ignite the air itself? This possibility terrified scientists, and a committee of 3 scientists were given the task of verifying this. C. Marvin, Edward Teller, and Emil Konopinski. They published the paper LA 602, Ignition of the Atmosphere with Nuclear Bombs, detailing this possibility and how they disproved it before the Trinity test. Today, more than 60 years later, LA 602 remains a beautiful example of scientific reasoning under extraordinary certainty. And in today's summer school session, we will retrace their journey to understand how they proved that the atmosphere will not ignite. Now, Sankeet will take over and give us a brief overview.
Good evening, all. So, from what Olive has explained so far, I guess you guys have an idea of the gravity of the situation they were in. The Manhattan Project was underway. It was weeks away from the Trinity test. For your information, the Trinity test was the first successful nuclear explosion in human history. And then someone asks an important question. The question was, what if the bomb not just destroy a city, not just kill thousands, but set the entire atmosphere on fire? A chain reaction propagating from the bomb outward until there is no atmosphere left. The question was so serious enough that a paper on this. They arrived at a conclusion. Today's session is going to be about that. Now, before we begin, we need to speak this we need to speak the language of its paper so that you guys have a better understanding. You guys have to keep in mind that this paper was written by three of the best physicists in the 20th century, and hence they did not stop to explain the terms they used, nor did they motivate any equations that was used. So before we begin, I would like to make you guys familiarize with a few concepts that will come handy in the later parts of the session. Okay, imagine that you're in a completely dark room. You cannot see anything, and you're throwing a tennis ball randomly in all directions. Assume that somewhere in the room there is an object, and you want to know how likely you are to hit it with a randomly thrown ball. What is the probability that you strike it successfully? Obviously, the answer depends on how big the object is. Yes, the size of the object. How much area it presents to you when you throw the ball. If it is a large flat ball, it is easy to hit. If it's a vertical ball, it's harder. If it's a single point, it's nearly impossible to strike that object. Now, this idea can be brought into nuclear physics as well. The probability of hitting the object depends on the area it presents. When it comes to nuclear physics, the object is not a physical barrier. Rather, it is an interaction. What if, instead of hitting a wall, you want to know how likely a moving particle is to interact with a target particle in a specific way? Maybe it will get scattered off, or maybe it will be absorbed by it, or a chemical reaction can happen. This probability can actually be calculated by assigning an effective area to each target particle. If the interaction is very likely to occur, the cross section is huge. If it is less, well, the cross section will be smaller as well. Now, you would have come across the idea of area of cross section in other parts of physics, such as electromagnetism, when you were dealing with flux. This idea of cross section in nuclear physics is quite different from it, because here it need not always be equal to the geometric area. If you look at the slide given here, in the first situation, the effective area is actually equal to the geometric cross section, that is pi r square. But in the other two cases, it may or may not be equal to that. It can be greater as well as less than that. In fact, the cross section is not really a property of the particle alone. It depends on the chemical reaction, depends on how much energy the particles have. The cross section is measured in a unit called barn, where one barn is equal to 10 to the power negative 24 centimeters square. Now, this idea will be used throughout the session, so keep this in mind. The next thing is something called Bremsstrahlung. Perhaps you would be familiar with this from your high school physics. We all know that an accelerating charge emits electromagnetic radiation because the accelerating charge disturbs the electromagnetic field around it. This disturbance propagates outward as a wave, as a radiation. Now, suppose you have a very hot volume of gas. The gas contains a large number of electrons and nuclei. Now, the temperature is large indicates that the electrons are moving at enormous speeds, at speeds that are significant fractions of the speed of light. As they are moving through the gas, they are constantly deflected by the electric field of the surrounding nuclei. So this deflection causes them to decelerate. As they decelerate, their speed decreases, their direction changes. This decrease in kinetic energy is actually released as electromagnetic radiation. Hence, we coined the term Bremsstrahlung for this phenomena. That is, EM radiation emitted when a fast-moving charged particle, such as an electron, rapidly decelerates or is deflected by another charged particle. This is a very crucial concept in today's discussion, because this is one of the major ways in which energy is lost after a nuclear reaction happens. A detailed discussion upon this will be done in the later parts of the session. So Keep this in mind. Now, a quick briefing of what today's discussion is going to be. First, we'll be discussing about the energy production during the bomb blast. When nitrogen nuclei in the air react with each other at extreme temperatures, they release energy. Well, how much energy do they release? How fast does it happen? Under what conditions? And why exactly did we choose nitrogen nuclei as the most probable candidate for this reaction? All of this will be discussed in this part. In the second part, we'll be talking about the energy losses involved. Well, along with the production of energy, the hot electrons in air are radiating energy away at an enormous rate. So can the production ever keep up with the loss? And is there any temperature at which the reaction actually becomes self-sustaining? And the third part is about a theoretical possibility. Setting aside all the physics involved, can any real bomb supply enough energy to heat enough air to even attempt ignition? So these three questions cover the entire architecture of today's session. Now Satvik will be taking over the session.
Yeah, so for any scenario, like for any kind of good scenario or a bad scenario, be it be helpful to humans or harmful to humans, the scientists always try to find out the ideal case because ideality in reality does not exist. But if we get the overview of ideal case, we can estimate the real chances of it happening. Similarly, in our atmospheric ignition case, we estimate the best ideal case. The best, as in the very absurd estimations, very high values of energies, and on the whole, the worst case, the best worst case scenario. Keep this in mind because this is the sole basis of the entire paper, the best worst case scenario. Imagine you own a business. Now, in order to run your business smoothly and earn profits, no matter what, you need data. Data of your products being sold, the costs, the production costs, the managerial costs, and all. Then you would need to assume some conditions, the worst possible conditions. Maybe some stock market crashed, or maybe some new virus and pandemic has happened, whatever. Even in such scenarios, your company should be able to thrive, at least able to maintain, not go into losses. In that way, you will be able to run your business smoothly. Similarly, the our atmospheric ignition scenario is no different than this business scenario. Essentially, the data we collect here is related to atoms, their energies, and the cascading effects. And we assume the worst possible condition. Now, in order to understand how we proceed, let us consider a system. A system can be an engine or a turbine or anything. It consumes some form of energy and it produces another form of energy. Now, if the consumed form of energy is greater than what is being produced, the system cannot sustain itself. If the produced energy exceeds the consumed form of energy, then the system essentially uses the produced energy to feed itself on and sustain. Our atmosphere in this case is the system. So basically, the energy produced in the subsequent fusion reactions should be able to sustain it and effectively release enormous amounts of energy and transferring the energy throughout the atmosphere, thereby causing the atmospheric ignition. Now, for the atmospheric ignition scenario, we have to consider two things: energy suppliers and energy consumers. Now, energy is primarily supplied by the atomic bomb. The then purpose of being built, the atomic bomb, and Due to its immense power and immense nuclear energy, it produces vast amounts of energy in within very few fractions of seconds, thereby raising the temperature to very high values. Now, this report talks about in such scenarios where the temperature has risen such dramatically, could the could the conditions be satisfied for subsequent fusion reactions and thereby igniting the atmosphere? From our lower classes, we have learned or memorized this thing about the composition of Earth's atmosphere. Earth's atmosphere primarily consists of nitrogen with 78%, oxygen 21%, argon 0.9%, and remaining gases. Now, in order for our best worst case scenario, we consider only lighter elements such as oxygen, nitrogen, carbon, and all. Why? Because their nuclei provide us the possibility of nuclear fusion, releasing tremendous amounts of energy. Now, out of those lighter elements, we have to choose particularly the worst element. Now, the worst element which we chose for our best worst case scenario is nitrogen. Why? Because it is unstable compared to the rest of the nuclei. Oxygen is very much stable. And even if we choose oxygen, its fusion reactions do not provide that much of an energy when compared to the nitrogen's fusion reactions. You can see two reactions being marked with arrows. One is a radiative capture, other is a alpha emission. Keep these reactions in mind as we'll discuss them in later slide and why these reactions are important. Essentially, the five types of reactions which can be possible were mentioned in the paper LA602, which are being showcased in the slide. Now, for fusion reaction to take place, the atoms or the nitrogen nuclei need to come closer. But you, from your plus one plus two education, you might have learnt about electrostatics, like charges repel. Similarly, each nitrogen atom consists of an electron cloud. So when they try to come closer, these electron clouds try to repel each other, creating some sort of Coulombic repulsions and a barrier between them. Now, the fusion can take place only after crossing this barrier or this fence gate. Now, this barrier is also known as Coulomb barrier, which is about 9.6 mega electron volts. Now, 9.6 mega electron volts seems like a harmless number, you think. But in order to understand that, consider the room in which you are listening to this session. Its ambient temperature is about 300 Kelvin. To put that into perspective, it amounts to an energy of 0.025 electron volts. Still not satisfied with this explanation? Well, take Sun's core, whose temperature is about 1.5 into 10 to the power 7 Kelvin. Now, that temperature corresponds to an energy of 0.0013 mega electron volts. So even the sun's core temperature is lower. The temperature which corresponds to such energies is lower compared to that of Coulomb barrier. The conversion factor I have written it down in the slide where one electron volt is equal to is implies 11,605 Kelvin. Now we have two possibilities. The colliding nuclei have energy greater than Coulomb barrier. The colliding nuclei have less than the Coulomb barrier energy. But you will ask, what is the energy of colliding nuclei? What are we considering? The energy of particle A, the energy of particle B, or both? Well, for a simplistic view, we are considering two particles A and B moving with velocities VA and VB. These velocities are less than the speed of light, although in our case they are very close to speed of light. For simplicity and explanation's sake, now from classical mechanics, Newtonian mechanics, you must have studied about systems of particles, and where for a two particle system, kinetic energy can be written as kinetic energy of center of mass plus kinetic energy with respect to center of mass. Now, we assume that no other forces act or appreciably change these velocities as and when they collide. So, linear momentum can only be changed due to collisions, and the only expendable energy is the kinetic energy with respect to center of mass. So, for our case, this energy of the colliding nuclei is essentially the kinetic energy with respect to center of mass. In reality, at speeds close to speed of light, conservation of linear momentum does not work. There lies a deeper concept which you can research about. Now, energy is greater than the Coulomb barrier. Yes, the fusion takes place with no hesitation. But for energy less than Coulomb barrier, in a classical sense, you think, yeah, they'll stop and no fusion takes place. But when one studies the laws and the absurdities of quantum mechanics, you will understand that these things are possible even at energies less than the Coulomb barrier. George Gamow, a scientist who proved that particles can tunnel through a barrier even when possessing less than the barrier energy, and through his Gamow penetration probability, he proved the probability of a particle penetrating through the barrier and essentially reaching the other side. Now we'll see how did he do that. Suppose the outside the target nucleus, they consider a stationary nucleus 1 and a particle is approaching 2. Now the Coulomb interaction potential is essentially V of r equals to z1 into z2 e square by r. Now their relative kinetic energy is less than the Coulomb barrier energy. So it should stop. But gamma tunneling probability says no. It can go. It can, not it must. In order to find out the probability, first he solved the radial Schrodinger wave equation where psi represents the particle wave function, the particle which is coming towards the target nucleus. Here mu is the reduced mass system. Essentially we are considering only two particles colliding. So we take the reduced mass of the system. We take the substitution psi of r equals to radial distance into capital R of r. On rearranging we get the following equation. Upon some mathematics and few other stuff, we get the solution psi of r equals to exponentially growing term plus exponentially decreasing term. Now, the exponentially growing term is discarded because the chance of the particle existing in the forbidden region itself is very low. It cannot always be positives. Like it cannot always be infinitely growing. So the exponentially growing solution is unphysical and discarded, thereby giving us the only exponentially decreasing solution. Here kappa is defined as square root of 2 mu times v minus e by h cross square. Now from your atomic structure, those who have studied plus 1 plus 2 might remember that probability density of a wave function is proportional to the modulus squared of wave function. So for our case, it is exponentially decaying function. So let us consider it is equal to some e power minus g. Now upon squaring and writing it down, we get e power minus 2g, where g is equals to integral of kappa dr. Dr is the small radial distance change. Basically, we are calculating in a spherical system, not in the xyz coordinate system. Now, for the integration to take place, we require the limits. The limits which we take are from the point at which the particle stops, because its kinetic energy has fully converted into potential energy, and it is not sufficient to cross the barrier. So it stops at a point greater than the barrier height and beyond the nuclear radius. Now that will be our outer limit. The inner limit would be the n- target nucleus radius, which is essentially the nitrogen nucleus radius. So from the nuclear radius to the point where Coulomb potential equals to relative energy, we integrate. We find this some sort of a weird integral which can be simplified using the substitution r equals to r2 sine square theta. Upon approximations, we arrive at the final result. G equals to square root of 2 mu times E by h cross into pi r2 by 2. Upon further rearrangements and all, we find the gamma tunneling probability is equals to the probability equals to e power minus 2 pi eta, where eta is equals to z1 z2 e square by h cross v. V is the relative velocity we talk, because we consider one at stationary with respect to one, the other is moving towards it for the nuclear fusion to take place. Now we have learned the fusion can take place regardless of the energy. If the energy is greater than the Coulomb barrier, yeah, it can happen with no hesitation. If it is less than Coulomb barrier, it might happen. We we got to know the probability of it being a successful reaction. Now, using that probability, we can find out how many reactions are taking place in a particular sample. Uh, how would we do that? Imagine you are traveling in a car. The chance of you crashing onto another vehicle is some p. Now, the amount of times you crash into other vehicles depends on the density of the traffic. If it is a heavy traffic road, the chances of you colliding with into other vehicles is higher. The probability might remains the same, but the density has increased such that there is now an increased number of collisions that can be possible. If the traffic itself is very low, you probably won't hit many or none at all. Similarly, reaction rate is also calculated in a way. The incoming number of particles per second times the probability of a hit. Now, previously we came across this term cross section area. Cross section area in nuclear physics is an essential measure of reaction probability. The more the cross section area, the higher probability that the reaction take place. And its units are 1 barn equals to 10 power minus 24 centimeter square. For our case, the nitrogen-nitrogen fusion reaction, there was a slight problem. There was no data for this collision reactions. Why? Because primarily the particle accelerators were not that capable enough to study these reactions, and secondly, this was not the primary focus of the research. The focus was mostly on developing uranium based atom bombs, hydrogen fusion based fusion bombs, and others. Nitrogen fusion was hardly of any concern. So, since we don't have any kind of information on cross section areas, the scientists began to assume, as usual, the best worst case scenarios. They took forth two types of models. The first being the constant cross section, or else every collision is effective basically. Every collision possible will result in a nuclear fusion reaction. But this is impossible. Why? It essentially states that you can ignore the barrier energy, and it does not depend on the energy of the colliding nuclei itself. The assumed value of the cross section is two bonds, but why did they do it? As usual, the best worst case scenario. Now, one point will strike to your mind, or I am striking it to you, that why did they choose two bonds only? If you calculate the radius of the nitrogen nuclei using the theoretical formulas, you will find out it is approximately equals to 2.9 into 10 power minus 13 centimeter. Upon using these theoretical values and calculating the cross section areas, we receive that it is 1.1 bonds. So, in order to overestimate the assumption and provide the best worst case scenario, they intentionally assumed it to be two bonds rather than the 1.1 which was calculated from theory. This means it changes a lot the calculations and the severity. Now, the second kind of model the scientist adopted is the not constant cross section, or not every collision is effective. The reality. If the energy is greater than or equals to the Coulomb barrier, yes, it definitely take part in the nuclear fusion reaction, essentially uh, contributing to the atmospheric ignition. But if the energy is less than the Coulomb barrier, we apply the gamma probability, the tunneling probability, where we multiply the constant cross section which we assume the two bonds into the probability. Now you would ask the why is the cross section itself changing? It doesn't make any sense. It will make sense. Now the cross section is an indicator of reaction probability, but the reaction probability itself is dependent on whether the energy is sufficient enough or not. So if the energy changes, the cross section should also change. Essentially, that's the reason we adopt this form when the energy is less than the Coulomb barrier. We have done with the collision cross section assumption. Now we have to find out how much energy after collision it releases. You have seen the five types of reactions which are possible, but you would ask which, like how many are taking first reaction, how many are paths are second and all. We don't know. At the time the scientists didn't know. Many different reactions are possible, different values. It's an absolute chaos. So they assume only 17.7 mega electron volts. Why? Because the ratios of different reactions, the probability of ratios of different reactions, it was not known at the time. And the 17.7 is the maximum energy produced. I asked you to remember the first reaction, radiative capture, which released even more greater than this alpha emission reaction. You would ask why didn't they choose that? Because it releases gamma rays. Gamma rays take almost the energy produced and they essentially escape the region of interest. They are essentially the atmosphere is transparent and cannot capture these gamma rays. So as always, considering the best worst case scenario, we assume the energy to be 17.7 mega electron volts per reaction. Now we are diving into more mathematical parts. So feel free to take screenshots or maybe ask ChatGPT after the session. Now the assumptions which we done, the cross-section models, the reduced mass systems, relative velocities, energy value assumption. Now we come to the number density assumption. Essentially the reaction depends on how many are present, how many nuclei are present. More the merrier, because more nuclei will lead to more reactions. and more catastrophic results. The scientists assume the number density to be 4 into 10 to the power 19 per cubic centimeter. Now, why that specific value? They gave a timescale argument. The nuclear explosion generally take place with order times of order 10 power minus 10 to minus 12 or 10 power minus 12 to minus 10, while the expansions itself take around like 10 power minus 8 seconds. Now, these are very small. When we try to observe, these changes are very, very tiny small. But when you compare both, the expansion of the gases itself takes more time. So, by the time the expansion take place and the pressure changes and the volume distribution take place, the explosion already would have happened, that the energy would have transferred already. So in such short span, the energy is given to the nitrogen nuclei. So essentially, the number density does not change appreciably in such time scale. Another thing which was utilized in the calculations was the Maxwell-Boltzmann distribution. You you would have studied this in your plus one plus two syllabus about this, and it's information about particles having more energy, less energy, and most probable energies. For our case, we will be using this equation because we are considering two particles, and two particle system includes the reduced mass system and the relative velocities. As a part of this session, I am giving you a task to find out why do atoms possess velocities as per Maxwell-Boltzmann distribution at thermal equilibrium. Why not any other distribution? If you find out any other distribution, you could give it your own name. In case you forgot, the reduced mass system is essentially m1 into m2 by m1 plus m2. We have completed the energy per reaction. Now, energy rate. Energy rate is equals to reaction rate into energy per reaction, like how many reactions are taking place and how much energy is being released. We have assumed the energy per reaction. Now we have to find out the reaction rate. Now, how do you find out the reaction rate? Let us look at a small, you would say, a past look towards kinetic theory of gases. The kinetic theory of gases in assumed two species of particles with number densities n1 and n2. Now, a particle with speed v is approaching the species 2. Now, in some small time, it will sweep a volume of v dt times sigma. Why sigma? Because it is the essential cross section area. Basically, around this area only the collision can take place. So, about this volume is covered by that's one particle. Now, in order to find out the number of species 2 present in that volume, we'll multiply n2 with the volume swept. Now, this is dn equals to n2 times sigma v dt. Now, in order to find out how that one particle from species 1 meets the rate at which it meets the species 2 particles, we'll divide dn by dt. Essentially, we are treating the operator as fraction, but at dt tending to 0, we'll, we'll get this n2 times sigma times v, basically rate of reaction per particle. Now you would ask for all particles, simply multiply it with n1 because n1 is the density of particles present. Thereby we get the collision rate density. But the above formula is not applicable. Why? The cross section changes, the velocities are not same. We assume that the whole sample follows the Maxwell-Boltzmann distribution, hence not every particle possesses the same velocity. Therefore, we do the averaging thing. where we average the product of cross section into the velocity over the entire velocity distribution. Now, this average is also known as thermal average. In order to find out this thermal average, we will be using our Maxwell-Boltzmann distribution, the probability density function, which is specified here. This Fv into dV essentially represents the fraction of molecules having speeds between v and v plus dv, where Fv is the probability density function. We have two models of cross section, hence we have to do two different calculations. The general formula for average is given here: integral from 0 to infinity sigma as a function of velocity times the probability density function for a small speed interval. Now for constant cross section assumption. The constant cross section assumption is essentially as the simplest one. So the sigma itself is constant, so we can take it out of the integration and integrate this v times fv dv from 0 to infinity. Upon doing the calculations, as you can see, the sigma is taken out of the integral and we find out that this whole integral value will come out to be the average velocity of the sample. So the result corresponds to two times the average velocity of the sample. Upon putting it in the energy rate formula, we get that energy production rate is directly proportional to square root of T. So as temperature increases, the energy production rate increases. Now for our variable cross-section assumption. For energy greater than or equal to Coulomb barrier, we have done the previously the calculation, which is essentially the constant cross-section assumption. But for energy less than Coulomb barrier, we have to use the gamma tunneling probability. Essentially, it's a variable cross-section. We define sigma to be as 2 times e power minus b by v, where b is defined as this 2 pi times z1 z2 e square by h cross. Upon pulling out all the constants and keeping the variables inside the integral, we get this v cube times e power minus b by v and e power minus mu v square by 2t times dv. Now this is a very complicated integral. If you want, you can try, those who are math nerds. But in no elementary antiderivative exists for this above integral. So they have to approach through different methods of integration, the numerical methods. The exponential consists of two terms, one due to Maxwell-Boltzmann distribution, one due to gamma probability. Now, if the velocities are very low, this exponential term, since v is in the denominator, as v is decreasing, the whole part increases. And basically, the low energy particles cannot cross the energy barrier. Thereby, the only possible reaction taking place is through tunneling. So the gamma factor dominates than the Maxwell factor, the exponential. Now, keeping this in mind, at low temperatures, a subcase in the variable cross section, at low temperatures, the reaction is possible only through tunneling. So we take the substitution x equals to b by v and calculate its derivatives as well and plug them into the integral, we get this sort of integral: x power minus 5 times e power minus x e power minus mu b square by 2t x square dx. Now, e power x falls off very rapidly compared to that other exponential. So the other exponential essentially almost remains the same. So we take an approximation of the other exponential, and using the Taylor expansion, which you have studied in 11th class limits, e power minus y is equals to 1 minus y plus y square by 2 factorial and so on, where y is this value. We approximate to only second term because beyond which the contributions are neglected. Now, on these two terms are plugged in and the calculation is conducted. We get that now this calculation is done using the gamma function, which is defined as gamma of n is equals to integral of 0 to infinity x power n minus 1 times e power minus x dx. Now using this gamma function we calculate, and the thermal average comes out to be t power proportional to t power minus 3 power 3 by 2 times exponential of minus constant by t. As temperature increases, this denominator becomes a huge value, thereby this whole fraction becomes a smaller quantity. So this exponential increases. So as temperature increases, there is a much higher probability of the particles fusing and conducting in and taking part in the fusion reactions. These calculations are conducted for less than zero point 0.2 mega electron volts temperatures. Why? Because the data shows that at such low temperatures, the energy possessed by them is so very low that only for means this that is through the tunneling probability. Now at the intermediary stages, where beyond the zero point 0.2 mega electron volt temperature, now the exponential terms which consists of these two, let us consider them as a function, as a whole function. So we'll get this. In order to calculate here, we use method of steepest descent. Instead of integrating the whole thing, we'll find out where the maximum contribution comes. Why we do this? Because the area under the Maxwell distribution and the area under the gamma probability distribution overlap at these points and give us a certain peak where the maximum contribution take place. So we'll try to find out that peak itself, the majority contribution. We differentiate this function which we have defined and set it to 0 to find its minima. This velocity is known as gamma peak velocity, and using Taylor expansion series around V naught, we find out the phi of V as in terms of the Taylor expansion series. Notice that the first derivative is missing because at first derivative V naught it's at first derivative V at V naught it becomes 0. Now using this Taylor expansion, we'll plug this in into this exponential, essentially approximating the integral, and we take out the constants out and we get this kind of integral, which is a Gaussian integral. This Gaussian integral has a result which is from minus infinity to infinity e power minus ax square dx, gives result root pi by a. Upon using the result and plugging in the values of phi and phi double dash, we get that the thermal average is proportional to a times t power minus 2 by 3 exponential of minus 3 times b square mu by 40 whole power 1 by 3. Now these a and b are numerical constants which are to be determined by the constants, pi values, the cross section values, other. Now, but is the nitrogen only the suitable candidate? The scientists asked. Could there be any other possible candidate that they would have missed? They began searching and they got an idea. What if the bomb is detonated near sea? It would release tremendous amounts of water vapor, thereby raising the probability of hydrogen nuclei, protons. Now, they conducted analysis on these protons and whether they could help in the reactions. And what they found out is hydrogen nuclei are definitely not sufficient to take part in the nuclear reaction. Why? First of all, the reaction cross sections itself were very small compared to that of nitrogen nucleus. And secondly, the reaction energies which were produced were very less compared to that of nitrogen. So essentially, they do not contribute much. And the abundance is also a question that even in detonating near the sea, in comparison to the 78% of nitrogen, it is always less. The hydrogen nuclei are always less than the nitrogen nuclei. Thereby, the possibility of other candidates were ruled out. After all these calculations, they plotted a graph. This graph is the is plotted due to the constant cross section assumption and the variable cross section assumption. The blue line indicates the constant cross section assumption line, which essentially is directly proportional to square root of t. Now the variable cross section. Notice it starts at some temperature and it will go on, and at very high temperatures they tend to meet. So these two model almost and produce the same results almost at highest temperatures. So essentially we learned how the energy is produced in a case of atmospheric ignition. But the production of energy is not sufficient enough. You need to understand how the energy is lost also. Now Olive is going to continue with the energy loss part of the session.
Now that we have seen in detail how the fusion reaction occurs and energy is produced, let us go into energy losses. Before that, I would like to define something called as the safety factor. The main goal of this particular section is to see that if the rate of energy loss exceeds the rate of energy production. And if it does, we are safe. So we define S, the safety factor, to be the ratio of the rate of energy loss to the rate of energy production. And we will check whether this S is greater than 1. Now, before we actually move into energy losses, one thing to note is that the explosion of the fission bomb produces high amounts of energy, as already mentioned. At these high temperatures, the extreme kinetic energy tears all orbiting electrons away from the nuclei. So instead of the atmosphere being filled with nitrogen atoms, oxygen atoms, and so on, we don't have full atoms, but we have what is called a plasma, which consists of free electrons and nuclei. Yeah. And if you've not heard of the term plasma before, it is the fourth state of matter that exists when there is very high temperature. Some examples of plasma include our sun, stars, and even lightning. And one thing that I would like to add over here is that because the temperatures are very, very high, it becomes difficult to keep using Kelvin. So what I will do is multiply the temperature by the Boltzmann constant, which is given on the screen, to convert the temperature into MeV units, where 1 MeV is corresponds to 1.16 into 10 to the power 10 kelvins. All right. Now that we have established that our atmosphere is in the state of plasma, we go back to the equation here. The, the nitrogen fusion producing magnesium and alpha particle, giving 17.7 mega electron volts of energy. This energy is in the form of kinetic energy that the product particles have. Now, how this energy is transferred is mainly by collisions. So these particles are not static in the atmosphere. They keep moving about randomly and they collide with each other. And that is how energy is transferred from the product particles to the surrounding particles. Now, since the mass of an electron is much, much smaller than the mass of the nuclei, energy is much more rapid between particles of comparable mass. So the energy from the product particles is first shared to all the nuclei, establishing a nuclear temperature. And electrons, because of their very low mass, receive this energy after many more collisions only. And therefore, the electron temperature is lower than nuclear temperature. Now, the rate at which the nitrogen nuclei transfer energy to electrons. The atmosphere has not only nitrogen nuclei, but also oxygen and other nuclei, but I will be considering only nitrogen as it is the most abundant nucleus. And we have this very fancy looking formula that is calculated assuming only the collisions of the nitrogen nuclei with the electrons. So the rate of this energy transfer is given as 4 pi times n. N is the number density of nitrogen in the atmosphere. Z in this case would be the atomic number of nitrogen. M is the mass of nitrogen nuclei. E is the charge of an electron. And we have a TE, which is the electron temperature, and Tn, which is our nuclear temperature. Now, as you can see here, this rate of energy exchange is proportional to the average of reciprocal of velocity. The bar above the 1 by v indicates average. As Satvik already mentioned, to see how the velocity is distributed at a particular temperature, we generally use what is known as the Boltzmann distribution. And in the Boltzmann distribution, our velocity average, reciprocal of velocity average would be root of 2m by pi times t electron. But our atmosphere, this region, is in a state of plasma, with high amounts of energy, high temperature, right? And so, also, one thing to note is the velocity here is the velocity of the nitrogen nuclei because they collide with the electrons. And so these nitrogen nuclei, they travel at huge amounts of speed due to the high temperature, almost close to the speed of light. What happens when you start moving near the speed of light? Relativistic effects start popping up. And to account for that, instead of the Maxwell-Boltzmann distribution, we use something called as the Maxwell-Eutner distribution. The name Eutner is German, hence the pronunciation. So according to the Maxwell-Eutner distribution, we have an equation that gives us the average to be 1 by c. C is the speed of light times 2 by pi theta. We define theta to be electron temperature divided by mc square. And As mentioned already, whenever I say temperature, I am using temperature in units of energy. So theta over here is a dimensionless constant. And you have the numerator depends only on theta, while in the denominator, you see something called an h. This h denotes Hankel functions. This is beyond the scope of this session. I've only mentioned it here because it will come up later. But you will see that these Hankel functions cancel out later on. If you're interested, you can always, I would suggest that you go and look up Maxwell-Ullner distributions. All right. Now that we have established that the atmosphere is in a plasma state, and you have free electrons and nuclei, what do you think happens? Electrons have negative charge, and the nuclei are basically made up of protons and neutrons. Neutrons, of course, have no charge, whereas protons have positive charge. And if you know already, opposite charges attract. So these electrons would be attracted towards the positive charge proton, nuclei. Okay. So our high energy electrons move towards the nuclei. And as they move towards the nuclei, distance decreases, which makes the force increase and the electron starts to accelerate, causing it to bend around the nucleus. Now, it is important to note that the electron is not directed straight towards the center of the nuclei, but at a perpendicular distance. And I will call this perpendicular distance impact parameter, denoted by B. And I will come back to that in just a minute. Okay. So our electron is attracted to the nuclei, and as it moves closer, because it's not directed to the center of the nuclei, it bends around the nuclei so that it can, due to the force, Coulombic force. Right. Now, according to electrodynamics, whenever a charged particle accelerates, it must radiate energy. And because our electron is changing direction, it is essentially accelerating. And this radiation, the power of this radiation is given by what is called as the Lamar's formula, where P denotes the power of radiation, which is equal to Q square times A square by 6 pi epsilon naught times C cube. Q is the charge of the particle that is accelerating, A is its acceleration, and C is the speed of light. And this radiation is given off in terms of photons. So this wavy line coming out of the nuclei is essentially the photon that is transmitted out. And obviously, this radiation has some energy, but then this energy cannot be created out of nowhere, right? And because of this radiation, our electron's kinetic energy reduces. That is, this electron slows down. Hence, this phenomenon of an electron slowing down is called as Bremsstrahlung radiation. Bremsstrahlung means braking. The name came because electron basically slows down or like hits the brakes. Right? So it is known as braking radiation. And remember, I mentioned I will circle back to impact parameter. And I said that the electron is not aimed directly at the center of the nucleus. But if it was aimed at the center of the nucleus, it would be a problem. And it may not even be aimed exactly at the center of the nucleus. If the impact parameter was small enough, or as it tends to zero, the radiation would tend to infinity. And obviously, we cannot have infinite radiation. It becomes a problem. This is where quantum mechanics helps us. Electron over here is not just a particle, but also a wave. Right. And we also use Heisenberg's uncertainty principle that tells us that you cannot know both the position and the momentum of the electron at the same time. Using that and in that, we say that the minimum value of this impact parameter has to be the de Broglie wavelength. Lambda here is the de Broglie wavelength, which is calculated as h bar by mu. H bar is reduced Planck's constant, and mv is the momentum. And using all of these formulas, Lamar's formula, Coulombic interaction formula, and this, you calculate this formula for the rate of energy loss due to Bremsstrahlung. Now, one thing, a side note sort of that I would like to mention is that Bremsstrahlung radiation is a continuous spectrum. As mentioned already, because of the existence of minimum value of the impact parameter, there is a maximum value that the radiation via Bremsstrahlung can take, right? But is there, say, like only this radiation can only take certain values? No. Because our electrons are free, they're not orbiting the nuclei, they're free, they can go anywhere they want. These electrons can take any values, like the velocity of these electrons can take any values, and therefore the energy difference is a continuous spectrum that goes from 0 to this maximum caused by impact parameter. And Bremsstrahlung radiation is a continuous spectrum. Now, coming back to this formula, so we have said that the rate of energy loss via Bremsstrahlung radiation is equal to 16 by 3 times Nz, where N is the number density, Z is atomic number, multiplied by Z square, E is again is charge, M is mass of electron, C cube and H bar, and you have the average of V multiplied by 1 plus E by mc square. And you might wonder, what is this 1 plus E by mc square? Where did that come from? Well, as mentioned already, this whole event occurs in a plasma region. There is a huge temperature, and we have the electrons moving really, really fast, right? So what we have to do is use something called a Lorentz factor. This 1 plus E by mc square is essentially the Lorentz factor, and we multiply that with the velocity, and then we calculate the average velocity using the Maxwell-Eutner distribution again, and we get this fancy equation where again theta is Te by mc square, and you have this Hankel function in the denominator. Now, if you noticed, the Hankel function in the denominator of the nitrogen nuclei to electron energy transfer and the Hankel function here is the same, right? That will help us in a little bit of time. And as Satvik had already mentioned, the average velocity by Maxwell-Boltzmann distribution would be root of 8t by pi m. And if we consider the temperature to be very low and remove all relativistic effects, then this 1.7 times root of electron temperature would be the rate of energy loss. So now our main goal of this session was to calculate the safety factor, right? But if you had seen previously in the slide that Satvik had shown, he used the nuclear temperature to calculate the rate of energy production, whereas almost everywhere here to calculate the rate of energy loss via Bremsstrahlung, we use the electron temperature. Right? This velocity depends on the electron temperature. So we try to see if we can find a relation between the nuclear temperature and the electron temperature. And to do that, what do? We assume that the rate at which the electron loses energy to Bremsstrahlung radiation is the same rate at which the electron gains energy from the nitrogen nuclei. And when we equate that, we get this really nice relation between nuclear temperature and electron temperature, which is only dependent on electron temperature and mc square. And you have this graph that shows is electron temperature with respect to nuclear temperature. And then we have the graph on the left where the y-axis represents rate of energy change and the x-axis gives us temperature. And as you can see, as the temperature increases, the rate of energy production and the rate of energy loss via Bremsstrahlung, they're almost the same towards like the very right of the x-axis, right? And from that, when we calculate the safety factor, we see that the safety factor reduces with nuclear temperature and we reach an empirical minimum of 1.6 at a nuclear temperature of 100 mega electron volts. Now, obviously 1.6 is not ideal. Yes, it is greater than 1, but it's not as good as we would like. But then if you look at 100 mega electron volts of temperature, that is about 100,000 times the temperature of our sun's core, which would make you think, oh wow, that is good. But when it comes to the end of the world, we have to be very pessimistic. So we will look at other energy losses too. And as mentioned earlier, we have a plasma region, right? And we've got these high energy electrons in this plasma region and also photons that are produced by our Bremsstrahlung radiation. Now, under normal circumstances, these photons would just get radiated away. But if you consider the volume of our plasma region to be big enough, then instead of just getting radiated away, these photons start colliding with these high energy electrons. And when they do that, the high energy electrons lose energy and photons end up gaining energy. This effect is known as the inverse Compton effect. Why inverse Compton effect? Because there also exists a Compton effect where high energy photons are scattered by low energy electrons. Now, because these photons are produced due to Bremsstrahlung radiation, there exists a relation between this loss due to inverse Compton effect and loss due to Bremsstrahlung radiation, which is given by 10 by 3 times electron temperature divided by mc square into r times lambda. Now, what is lambda? Lambda over here is the Compton mean free path. And if you don't know what a mean free path is, it is basically the average distance that a moving particle travels between successful collisions. In this case, it would be the distance that a high energy electron would travel before it goes and hits a photon. Right. And this Compton mean free path is known to be 42 meters. And because this inverse Compton effect is directly proportional to the radius of our plasma region, we will now see if what is the optimal value of this plasma region should be. Now you might wonder, why do I say radius? Why couldn't the plasma region be, say, a cuboid or any other shape? Well, we assume that this region is a sphere because of symmetry and to make the lives of physicists easier. Now, the next energy loss would be we've said that there is a plasma region, right? But then the air surrounding this plasma region would be at normal temperature, and then the energy would be transferred to the volume outside due to collisions. So when particles inside this plasma undergo like random motion and they collide with each other, and when they leave this region and collide with a particle outside, they transfer energy to the surrounding air. And so for our nitrogen fusion reaction to be self-sustaining, a new fusion reaction must occur before the energy can be diffused away. Right. And that is what we will consider in this section. Now, what we will do is, even though this plasma region has photons, electrons, and nuclei, we will consider photons to diffuse the energy outside, because most of this diffusion occurs by photons. And the photons don't just move from inside this plasma region sphere outside in a straight line. They collide within the sphere itself, and after multiple collisions only they move out. And when you take the r to be the distance that the photon actually travels before it moves out, then you can calculate d escape, which is the actual distance that the photon would travel after multiple collisions. And you have this formula that gives us d escape equals to r square by lambda, where lambda again is the mean free path between collisions. That is the average distance between two consecutive scattering collisions that happen within the plasma region itself. And you calculate diffusion, which is the fusion mean free path, which is calculated as 1 by n times sigma, where n again is the number density and sigma is the cross section. Uh, so essentially, we equate this d escape to the diffusion to calculate what the minimum value of radius should be. And when we do that for the nitrogen fusion reaction giving magnesium and alpha particle, we find out that the radius is 57 meters. Now, to produce a plasma region with say a nuclear temperature of 10 mega electron volts, I'm using 10 mega electron volts instead of 100 mega electron volts, because if you had noticed in the graph earlier, the safety factor at 10 itself was 2, right? And 100 is way too high for this. So we'll assume 10 mega electron volts. And when we do that, we find out that we will need 1.5 times into to 10 to the power 6 kilograms worth of material to create such a plasma region. This obviously is too high. So then we try to see if we can somehow reduce this radius. Now, the lambda used in d escape is obviously a constant, and number density is also a constant. So the only way that we could reduce radius is by reducing this sigma. So in the second equation that I have given here, what happens is nitrogen fuses to form oxygen and carbon. And in this reaction, the nitrogen nuclei do not actually need to come into contact. One nitrogen nucleus splits off deuterium nucleus that then attaches to the other nitrogen nucleus, forming oxygen and carbon nucleus. Right. And we see that the radius from such a reaction would be 7 meters. Is this a problem? Well, no, because the amount of energy that the second reaction gives is only 10.6 MeV. So our safety factor, when multiplied, is increased by a factor of 1.67. And with that, we come to the end of the energy losses. But as I've mentioned here, is it possible to create a bomb that has this huge radius, 57 meters, and that could actually ignite the atmosphere? Sanket will take over from here.
Yeah. So till now, Olive and Satvik has been speaking about the energy production as well as the energy losses that are involved in the nuclear explosion. So the next part of the discussion is going to be, what if we could at least theoretically make a bomb that can set the air on fire? So before we go into that, let us go back to some thermodynamics which you would have done in your high school. Suppose that you have a fixed amount of energy Q. Why a fixed amount of energy? Well, even if a nuclear bomb releases a very huge amount, it is still limited because it depends on the chemistry of the nuclear material that is being used. So your energy, even in this case, is still finite. The temperature change that can be produced with a fixed amount of energy is inversely proportional to the quantity of the matter that is being heated. Is inversely proportional to the quantity of matter that is being heated, which is quite clear from this relation given here. So the temperature change is inversely proportional to the volume being heated. Now you may think that if we minimize the volume, well, the temperature change that can be brought about by a fixed amount of energy, it can be increased, right? As the denominator goes down, delta T here goes up. Yes, that may seem obvious, but actually that is quite a naive conclusion to arrive at. That is because the propagation of the reaction demands that the energy production in each newly entered region exceeds the losses from that region. What does this mean? Well, let me break this down for you. See, when a nuclear reaction happens, energy is produced as the nitrogen nuclei collide and fuse with each other. This energy, well, it is lost primarily through Bremsstrahlung as well as other modes such as inverse Compton effect. The energy that is produced, it is actually carried away by the product particles, primarily the alpha particles, who have an initial kinetic energy of approx 17 mega electron volts. These alpha particles, they travel outward from the reaction site and gradually deposit their energy into the surrounding medium. What do you mean by this deposition of energy? Suppose a fast charged particle, in our context, an alpha particle with about 17 mega electron volts of kinetic energy, it is fired into air. Now, it does not travel through the air like a bullet fired into empty space. Rather, it interacts with the other particles around it. Now, it constantly feels the electromagnetic forces that are acted upon it by the other particles, and these interactions slows it down. However, is this loss uniform or does it follow some pattern? This actually determines our argument of whether the temperature change can be attained by heating a very small volume. See, initially, when the alpha, right after the reaction, when the alpha particles are produced, they have a very high kinetic energy. But when the alpha particle is moving very fast, it moves past each electron in a very small fraction of a second. The electron barely has any time to interact with these alpha particles and respond. Hence, a fast particle loses energy slowly per unit distance. Now, as the alpha particle moves, it slows down because its interaction with the surrounding particle increases and it loses energy more rapidly per unit distance. If you look at this graph, you can see that this graph here represents the rate of loss of energy of the particle as it moves through a medium. This is called the Bragg curve, named after the British physicist William Bragg, who did the calculations and arrived at a result in the early 1900s. On the y-axis, we have here the stopping power, which is nothing but the energy released per unit distance. Well, just after the reaction, the alpha particle has a very high kinetic energy. However, the energy that it releases per unit distance, it's low and roughly constant. As it proceeds, this increases and reaches a sharp at a particular distance, and then it comes to rest as it turns into a neutral helium atom. This is because at different intervals, the time with which it interacts with other particles is different. This introduces us the concept of interaction time. The interaction time is basically the time that a moving particle spends near another particle, such as an electron or a nucleus. As far as we are concerned, the physical quantity that matters to us is the path length. That is the distance that the alpha particles move before they come to rest. So this distance is actually called the mean free path or the range of the alpha particle. Now, this So the conclusion that we have arrived at is that the alpha particle does not actually deposit all of its energy right at the reaction site. Rather, it moves a particular distance and gradually deposits all of its energy, deposits its energy, and most of it is deposited at a particular distance away from the reaction site. So our initial argument was that if the volume is brought down extremely small, the temperature change can be huge. However, that argument is not valid because the energy is not actually deposited only at the reaction site. So our question changes to how much energy does it take to heat a sufficiently large volume to the required temperature? In order to know that, we need to understand how big that required volume is. For that, we need to find out the value of the range, that is lambda here, which is equal to 1 upon n times sigma total. Here, capital N denotes the density of particles in the air, and sigma total is the cross-section area that the particles present for the interaction. Now, to calculate that, we need to find out some relation that would give us the total area of cross-section. So when the alpha particle passes an electron, the energy transfer to the electron in a single collision, it depends on the impact parameter B here, and also the another fundamental result in the charged particle scattering in the Rutherford cross section. That is, when a particle of charge Ze passes near an electron of charge E, the differential cross section for scattering into solid angle, that is d sigma by d omega, is given by this equation. And also the energy loss per unit distance, it can be found out from these results, which comes from plasma physics actually. And underlying beneath all this is another concept called the Fokker-Planck equation, and by using some other relations from thermodynamics, we finally arrive at a particular equation for finding out the area of cross section. Now, I would like to motivate you guys to read more about plasma physics and the equations that are actually involved in this derivation for the area of cross section. So finally, we arrive at this equation where sigma E, that is the total area of cross section for Coulombic interaction between the alpha particle and the electron, turns out to be this particular equation. Now, as Satvik mentioned earlier, what we are considering is the best worst case scenario. That is, we are assuming that the explosion takes place in the worst possible manner and the maximum energy is released. For that, the area of cross section also needs to be maximized. So we differentiate this equation and set it to 0. From that, we get that the relation is maximum when E is equal to 9 by 2 times TE. Here E is the energy of the alpha particle and TE is the temperature of the electron in the air. So the maximum value of the Coulombic interaction between the alpha particles and the electron is given by this relation. Now, apart from this, the alpha particle is also undergoing nuclear scattering because of the nitrogen nuclei that is present in air. This also provides area of cross section, which is approximated to about 1.2 barns. So the total area of cross section that is in front of the alpha particle is about 3.3 bonds. Now, as mentioned earlier, this is a bit exaggerated value, but we are considering the best worst case scenario. So now we have the value of sigma total required to calculate the range. If we plug in this value of capital N and sigma total, we will get that the range of the particle, that the alpha particle, is about 57 meters. What this means is that the alpha particle travels an average distance of 57 meter before it actually deposits most of its energy. So its energy is not actually deposited at the reaction site itself, but rather at a distance of 57 meters away from there. What does it imply? Well, it implies that you need to heat up a volume or sphere of radius 57 meters such that the reaction is sustained and it propagates in order for the atmosphere to get ignited. However, for such a huge volume of air to be ignited, you would be requiring an enormous amount of energy. That volume of air would approximately have about 4 into 10 to the power 31 nuclei, 3 into 10 to the power 32 electrons. And in order to heat up that volume of air, you would be requiring energy of the order of 10 to the power 32 mega electron volts. But a fission bomb produces a maximum of 5 into 10 to the power 26 mega electron volts of energy. And that too only if the reaction is 100% efficient. Typically, nuclear reactions have an efficiency of around 1%. And even then, you would be requiring a mass of 1.5 into 10 to the power 6 nuclear material for all of this to happen. Now, all of this is actually far from achievable. Hence, the physicists arrived at a conclusion that it is quite impossible to build a bomb that could set the air on fire. But is this the only threat? Well, the answer is no. If you have watched the movie Oppenheimer, you would remember this scene where physicist Stella proposes an idea of building a fusion bomb, that is, a bomb made of heavy hydrogen, deuterium. See, a bomb powered by fusion, on paper, it releases more energy per unit mass than fission. So why not proceed with that one? Well, the thing is that in a fission bomb, it is very efficient at depositing energy back to the surrounding such that the material keeps the reaction self-sustaining. But deuterium nuclei, they are lightweight, low charged particles. They don't radiate efficiently when they collide or interact. So the energy from fusion reactions does not help in reheating the way which is done in fission. Now, another thing is that for an amount of 6.4 mega electron volts of energy to be released per deuterium, all of these secondary reactions need to happen. The probability that these reactions happen is actually quite low, especially the last part where a triton combines with the helium-3. And even if all of this were to happen, in order to heat up a required volume of air, you would be requiring a sphere of radius 3 meter of liquid deuterium, which was not feasible. Hence, we closed that pathway as well. Now, another possibility. Earlier in the session, Satvik had discussed about all the possible reactions that could happen. Out of this, the oxygen-carbon channel actually seemed quite a bit dangerous at first glance. Why is it so? Well, it was mentioned by Olive earlier that in this case, their range is approximately 7 meter. See, I mentioned that the range for alpha particle was about 57 meter. It drops down to about 7 meter in the case of oxygen and carbon channel. What does this mean? This means that the volume that you need to heat up, that also decreases by a factor of R cube. That is 57 upon 7, the whole cube. So on first glance, this may look catastrophic, but it did not cause much of a worry. The reason for this are mentioned here. The first one being the Coulomb barrier. For this reaction to proceed through this channel, it had to overcome a Coulomb barrier of approximately 14 mega electron volt. Now, to put this into perspective, the Coulomb barrier of the alpha particle path was about 7 to 8 mega electron volts. Now, you can argue that, well, the Coulomb barrier can actually be overcome by quantum tunneling, which is a possibility that Satvik discussed. But the thing is that the quantum tunneling probability, it is proportional to e to the power negative root over b by t. Here, the capital B is the term that is representing the Coulombic interaction. Oxygen and carbon have comparatively higher charges, and hence the Coulombic interaction is more. Hence, the quantum tunneling probability is reduced. The second reason for this path for not being such a dangerous one is that the energy released per reaction is smaller. The energy released per reaction is about 10.6 mega electron volt, which is less than the 17.7 mega electron volt of the alpha emission pathway. This increases the safety factor by a factor of about 0.6, making it to 2.67. The third one is the inverse Compton effect. It was discussed a bit in detail by Olive, and further clarity will be given by Satvik.
Yeah, so the Compton scattering, we have seen the energy production rates, the energy loss rates, how the energy is produced due to the fusion reactions, how it is lost due to Bremsstrahlung radiative losses. There is another thing, the Compton effect. The Compton effect is through which the electrons, high speed moving electrons, transfer their energy to the photons, which in turn escape. Basically, they lose out the energy. The inverse Compton effect is essentially the inverse of it, where photons transfer the energy to the electrons. Now, this inverse Compton effect is very critical because inside the fusion region, where the electrons are carrying the energy, they can escape out the region and essentially transmit away the energy. Now, the photon carrying the lost energy, if it comes back and due to inverse Compton effect, it transfers this energy back into this region, it stays for quite long time, then the losses can be minimized. And the scientists worried about this possibility, whether this inverse Compton effect could significantly reduce Bremsstrahlung radiations. But when they found out and did the calculations, that the calculations resulted that the photons event when the high speed photons ga- gain very much high energies, they essentially escape out of the region instantly. So the chances of them transmitting back into the region are very less. Thereby, the inverse Compton effect, though existing, does not significantly reduce the Bremsstrahlung radiation. Hence, in the first graph, you see the green color line, which represents the Bremsstrahlung loss rate, is always greater than these two production rates. This ensures that the reaction region does not reach to a point of ignition temperature or the nuclear temperature where it cascades into a chain self-sustaining chain reaction. Upon all these evidences, calculations, and assumptions, in conclusion, the LA602 report established that the Earth's atmosphere cannot be ignited by fission or a thermonuclear bomb, essentially making it a dream. Even after conducting such in depth research, the scientists were still terrified of the probability of a near zero probability of an atmospheric ignition. The first atomic test, the Trinity test, on July 16, 1945, many scientists were still pondering over the question whether the atmosphere would ignite and the world would get destroyed. As you can see, the world did not get destroyed, and the first nuclear test was conducted very successfully. Hence, by through the conclusion of the report, we can sufficiently sleep at our homes that the atmosphere could not be ignited due to a mere atomic explosion. This report is also a kind of an overview of how scientists meticulously create the worst possible outcomes for disasters and try to overestimate their chances so that they can find out what in what ways they can reduce the damage caused. Thank you for attending the session. We hope you learned something today. And feel free to drop any questions in the WhatsApp group. You can scan the QR for the attendance. Once again, thank you very much for attending the session. We will be ending the live stream in 2 minutes.